in this case, what we have is we've got an unidentified compound, and we need to work out the empirical formula. What we have in terms of elements, we've got carbon, hydrogen, oxygen. And so how am I going to approach this? Well, the first thing I'm going to do is I'm going to take a look at the percentage composition by mass. And in this particular case, if we add those up, this is the first thing I'm going to do. Just a quick check. I'm going to add these up and see what number we come up with. So this is for carbon, we've got 51.43. And then hydrogen, we've got 2.86. And for oxygen, we've got 45.71, right? So I would invite you to have a go, see what you come up with when you add those up. If you did try that, what you should end up with is 100, right? Okay, so at this stage, I've got some level of confidence that, okay, well, the total percentages of these. So sometimes, why this is relevant is sometimes this actually doesn't add up to 100 exactly. That doesn't mean you can't work out the empirical formula from it, but it can be valuable to have a baseline idea of what you're actually working with. Okay, so how are we going to actually access the problem in terms of comparing the quantities as we would need to work out the empirical formula? Well, in this case, the equation I'm going to be using is the equation that relates amount of substance to masses, right? So that is N equals M over MR, right? So that's mass in grams and MR, so that's molar mass, and that's in grams per mole. Yeah, it's kind of a bit diagonal, but you get the idea, right? So but right now we have percentages by mass. We don't have a actual, I don't know, like a concrete mass. A concrete mass is not given in the question. And because of that, we're going to actually use an assumption as a tool to kind of make progress in this problem. So the assumption we're going to use is we're going to assume that we've got a specific sample, and that specific sample is a total of 100 grams, right? And so that if we make that assumption, given what we've seen, therefore on the basis of that assumption we can say, okay, so for carbon, right, for carbon we've got 51.43 grams. For hydrogen we've got 2.86 grams, and for oxygen we've got 45.71 grams. Okay, now beyond this we would need, in order, so my aim that I'm thinking about is, okay, well, how do we actually get this to the amount of substance? We've established what equation we're going to use. What's missing? Well, we need, as the equation shows, we need to use the molar mass, right? We need to get the molar masses, use those to get to the molar quantities that we can use to establish an actual ratio that we can work with. So in order to do that, we're going to take a look at the periodic table. I've got some excerpts from the periodic table here, and the relevant ones: carbon, hydrogen, and oxygen, right? So if I just go back here a little bit, and okay, so the MR, these are very common elements, so probably already know these elements, like what their relative atomic masses were, but just for the sake of comprehensiveness, I'm just going to kind of go through these steps and okay, so for carbon, so right, MR of carbon is going to be 12. MR of hydrogen is going to be 1. And MR of oxygen is going to be 16. Right. One of the other things which is actually quite valuable when it comes to just writing these down, even if it's a case where, okay, but I think, let's say a situation is you say, well, I think I already know what the relative atomic masses are of these, I don't need to write them down. One of the reasons why it can potentially be valuable is when you show your thought process as you're writing this down. Let's say later on you kind of made a mistake somewhere, or someone noticed you made a mistake somewhere, and they're looking through what you've written. They could kind of look at it and say, okay, I see this is where the mistake came from. Like, for example, let's say you had accidentally, maybe you put 24, you divided carbon by the mass of carbon by 24 for not a very clear reason, but you just chose it, I'm going to divide the mass of carbon by 24 instead of 12. If you had written the molar mass of carbon is 12, and then you went on to divide the carbon by 24, then it's like, okay, well, you knew what the molar mass of carbon was, you just made a mistake afterwards. But if you mistakenly had thought the molar mass of carbon is 24 and not 12, it could raise much more serious questions, right? About, okay, does this person know, the left from right, right? So, but anyway, let me not get distracted by those considerations at the moment. But you see the molar masses there. Okay, so I'm going to divide these numbers by the molar masses. So carbon, we've got 12, so it's going to divide it by 12. Hydrogen, we've got 1, so we're going to divide that by 1. And you can see what the answer is. So anyway, oxygen, we're going to divide that by 16, right? And now we can say, okay, we're going to actually establish a ratio of moles. So N equals but this is like the ratio between them, between carbon, hydrogen, and oxygen, right? So the first one, 51.43 divided by 12, it's going to be 4.28583, and that is going to be in a ratio of course this is divided by 1, so you kind of know, okay, the answer for this part is going to be 2.86, right? It's not going to, one's not going to change what the answer is. And in this case, 45.71 divided by 16, right? And that gives us 2.85688. At this stage, if you're looking at these numbers, you will notice that 2.86 and 2.85688. If you were looking at these numbers to 2 decimal places, they're basically the same number, right? I mean, that's what they are. But I'm not going to do any rounding at this stage. So for the purposes of progressing the question in line with what's currently here, sans, without rounding, I am looking at it from the perspective of, actually the moles of oxygen is slightly less than the moles of hydrogen, right? Despite what you might read into by looking at the rounding. Okay, but of course the similarity has some other implications which we will get to later in the question. What we're going to do is we need to divide both, not both, but all three. We need to divide all three by the smallest number among them, and this is to serve the purpose of trying to establish a whole number ratio, right? The empirical formula is the simplest whole number ratio. So we're looking at, we're trying to establish that. Okay, so when we divide, at least when we divide this by itself, which is the smallest one, divide that by 2.85688. We know that at least one of these is going to come to a whole number, right? It's going to be, that one's going to be 1, right? So, okay, so let's do the other one. So, and then this one as well, 2.85688, right? And so at this stage, invite you to have a go, see what you get when you work those out. And if you did that, what you should find is for this you get 1.50018. For this, you're gonna get 1.00109. And here you're just dividing a number by itself. So of course, in this instance, we're going to get 1, right? So looking at these three numbers, do we have across all of them what we could reasonably say is the simplest whole number ratio? Well, we look at this one at the end. This is a 1, yes, so this is a whole number. However, in this case, if we look at this to 2 decimal places, we could say, yeah, well, we've got a whole number. But at this stage, I'm not looking to do aggressive rounding with this, when we have a number outstanding on the other side, which we can quite clearly see is not particularly close to a whole number. It's basically roughly in the middle, right? It's 1.5 effectively. If we were to round it to like 3 decimal places or 2 decimal places or 1 decimal place, it's 1.5. So at this stage, because we've done the division and we still don't have a whole number ratio, we need to do some scaling up. And so in this case, what does a scaling up look like? Well, scaling up would effectively look like, well, let's multiply it by integers, increasing step by step until we get to an integer where such that when we multiply all 3 numbers by that integer, we get what effectively would amount to a whole number ratio. And it's the lowest number that can achieve that as far as increasing integers. So we start from 2, 3, 4, 5, 6, etc. So we would cycle through that. The number we would start with in this case would be 2, right? And if we multiply all the values here by 2, what do we get? So let's try that and see if we need to increase to multiplying it by 3 or 4, or if 2 might just be sufficient. So if we multiply all of these, but I'm just going to put in brackets, that's going to just be multiplied by 2. Here we're going to get 1. No, well, not 1. We're not going to get 1. We're going to get 3, right? We're going to get 3.00036, right? In the middle here, we're going to get 2.00218, and here, well, if we multiply 1 by 2, what do we get? I don't think we need a supercomputer for that, but that would give us 2. Okay, so this now looks much different to how it looked before. Before we had literally a 1.5 in there. Now we have a 3, a 2, and a 2, right? So just based on looking at it, like from a perspective of, well, if we were to round this to 2 decimal places, what are we gonna have? We're gonna have whole number ratio. Is it the simplest whole number ratio, right? So let's do that rounding, and then we'll ask that question. So at this stage, because of how close this is to a whole number, especially when when we do the rounding to even 2 decimal places, it becomes a whole number, and it becomes an integer. So we're going to do that rounding, and we're going to get 3, 2, 2, right? And is this the simplest ratio we can get? The simplest whole number ratio we can get? Well, I would say in this case, yes, it is the simplest whole number ratio we can get. So in this case, the formula would be effectively, so this is carbon, let's see, carbon, hydrogen, oxygen, right? So C3H2O2, right? C3H2O2. So this would be effectively our empirical formula in this particular instance. All right.